Well, welcome back, and let's continue. So, yeah, we have discussed that. All right, there are so many super hashes, and they're not equally important. This is mainly because the position of the FIQ or Q's project on that one-dimensional projection, or on the position regarding to the boundary of the bucket. Does affect the probability of where its nearest neighbor would appear. If we look at the example here, say this is FQ, and as long as we move it from the rightmost to from the leftmost to the rightmost, we can see that. All right, this part, because again, the probability of or the distance between FQ and the FO or FO star follows the normal distribution. All right, so here the numbers are the integration of this two red area and this gray area, but these are not the actual the actual number. It's just an illustration. All right. So now let's look at it. So the gray area is the cumulative probability that O star and Q O star will fall into the same bucket as the query. Right. And this right side red area is where the O star will fall into this bucket from 0.5 to 1.5, and this left area is to fall into this part. So this is HQ plus 1, and this is HQ minus 1. Right. So as the Q moves, the Q's projection or FQ moves, you can see the probability, the cumulative probability actually moves as well. So, for example, if Q is here, then apparently, if O is not in the same bucket with Q, it would be in have a much higher chance to fall into the right bucket next to Q, next to Q's, rather than the left bucket. But if Q falls here, then things turns differently, turns oppositely, right? Now we consider the case 1k equals to 2. So we have two hash functions, so hi1 and hi2. Right. So let's say this is hi1 where the Q lies here, and this is hiq where the Q is here. So apparently, the most possible position for Q's nearest neighbor would be hi1q and hi2q. So it's here and here. So all falls into the same bucket as the query. And what is the probability? We do the multiplication of these two because they are independent, right? So you times 0.5 with 0.63, you got this number. Right. Then we could we could compute all the probability that HO would force into say for different combination of HIJQ, HIJQ plus 1, and HIJQ minus 1. Right, and it is so as you can see, the next one should be using this times this. Right, it's hi1q and hi2q minus 1, and next one should be this one times this one. Right, it's hi1q plus 1 and hi2q, and so on and so forth. And you can see the probability are decreasing, right, in the decreasing order. So basically although we have 3 to the power of k different possible super hashes for queues nearest neighbors to force into, we do want to visit them following the probability. So we start from the most likely ones, followed by the less likely ones. In this way, we can speed up the whole processing. All right. And in real applications, we don't have to compute the integration because it is time consuming. Instead, we use the offset between FQ and the boundaries, like this and this, to do the computation, to help compute the order here. It is well, the operation here is the reason here is straightforward, right? Because the relationship between the integration of this part is closely related to here the distance or the offset between Q and its boundary. All right. So we won't discuss more on that topic. And now let's look at the advantage and disadvantage of multi-probe LSH. So the good thing is that it requires less L because it uses hash tables more efficiently. So it no longer needs that much L. So reducing number of L also reduce the number of the space cost and the time cost for the index construction, right? And also it is more robust against those unlucky points, where those points that should fall into the same bucket with the query, but it doesn't, right? So this is the good thing about using multi-probe LSH. And for the disadvantages, multi-probe LSH actually lose the theoretical guarantee about the result. So although we have not discussed this, but I think it was mentioning here. So it's more like an engineering solution to improve LSH. Right. And also it is not parallel friendly, in the sense that you can imagine, I mean, if you if we parallel the task by, say, for each worker we use a single hash table, then multi-probe LSH actually requires less L. So but on each hash table it uses more time to probe, right? So assume we have enough resource, then using multi-probe LSH, we probably reduce the number of L from 10 to 5, but on each node, the time could raise from, let's say, 10 seconds. Maybe it will increase to 50 seconds, right? So then the total time would be, because it's a parallel work, so the total time is determined by the maximum one around all the nodes. So it's not good. On the other hand, if we say we divide or partition the data, right? Not the not according to different hash tables, then the problem is even worse. Since in LSH it's just a hash, you find it, then it is there. You didn't find it, it's fine. But in multi-probe LSH, you does not just look at the buckets that the query lies on falls into. You will also probe the adjacent buckets, where these adjacent buckets could, if we say partition the data, the adjacent hash buckets or the data in that bucket could be partitioned into different partitions, say in different machines. Then there is a communication between machines, which is which is exactly what we need to avoid when we design a parallel work or a MapReduce work. Right? So in multiprobe LSH, it is not parallel friendly. Now we look at another improvement of LSH. So it is called a collision counting LSH, or for short, C2LSH. So C2LSH is from Sigma 12. This is the original paper. I listed here because we need to implement it in our project 1. All right. So project 1 is to implement this algorithm using PySpark. Now we will use some time to introduce project 1 at the end of this session. But for now, let's look at the algorithm first. All right. So the observation or the motivation of C2LSH is, let's use an example here. Say, make your own guess. Say which one is closer to Q. Let's say the number is just the hash value. So this is this is hi1x, h11x, h12x, and so on and so forth. This is h21x, h22x. This is h31x, h32x, and so on and so forth. All right. So these are the hash number of Q, and these are the hash value of O1 and O2 respectively. Now, which one is closer to Q? Just based on the numbers here. Right. I think most of you would guess that or would say that O1 should be the one closer to Q. Because for O2, you can see there are hash values of 3, even 4, which indicates that Q2 could be far away from the query. And for O1, it's got most hash values that is same as Q's, but it is unlucky that for each group or for each super hash, it has one hash value that is slightly different to Q's hash value, which, however, for O2, it gets lucky that for the first super hash, it has exactly the same hash value to the query. All right. So most likely, this O2 would be a false positive, and this O1 would be a false negative. But for LSH, it actually will include O2, but exclude O1. Right. Both things are not good, are not what we want. Right. Well, so this is the motivation of C2LSH. And in order to overcome this drawback of LSH, as you can see, I mean, I think most of you has already got some idea, right? Because see, O1, the problem here is in LSH, it actually divided these hash functions into different groups or different super hashes. And even one mismatch in a super hash will lead to a mismatch of the whole super hash. But LSH does not consider, for example, O1, the total number of matched hashes to the query is 9, right? And for O2, it's just 5. So this kind of statistics is ignored by the original LSH. So by collision counting, you just count the number of collisions. Well, collisions actually means the number of equal hashes of O1 of the data and the query to determine which should be the candidate of the query. Right. So the paper itself, because it keeps the theoretical guarantee of LSH, so the paper itself has a large part of theoretical analysis and mathematics. Due to the time limitation, and also it's not the essential part of this course, so we will omit the theoretical parts. So in order to, because of that, we have to do some slightly or minor modifications on the original version of the paper, of the algorithm in the paper, right? So that's why, I mean, for the project, please stick with the algorithms that described in this lecture, in the slides, rather than in the paper. Right. Although, I mean, the essential ideas are the same, and the result won't change a lot. I kind of simplify the original algorithm, so you are only required to implement a light version of C2LSH. Now let's look at the idea of the algorithm. So as I have mentioned before, the idea is to count the collisions, where the collision is a match on a single hash function, which in LSH is Hij is Hij, right? And in C2LSH, it will become Hij, Hi, because there is no L thing, no group thing. Right? We don't group k hash functions together as a super hash function. All right, and then we use the number of collisions to determine the candidates. And apparently, I mean, the more that the number of collisions is, the more possibly that the node, the data would be the nearest neighbor of the query. All right. So again, in LSH, we need them to match one of the super hash with the query, but now we want them to collide at least alpha m hash values with the query. Right. So m is the total number of hash values. M is the number of hash values, hash functions. So alpha is less than 1. So basically, we want them to collide at least a fraction of the total number of hash values with the query. So it becomes a candidate. So in LSH, the probability of O with a distance to Q that is smaller than R1, which means O is a near point, the probability of O is a nearest neighbor candidate of Q is this, as we have, it's at least this. So as we have mentioned before, right? Now we want to compute the case with C2LSH. So this is the only mathematic part in today's lecture. I mean, we have to do this to give you some initial ideas of why it works, right? And hopefully the mathematics here is not too hard. Now we consider any point O with a distance to Q that is smaller or equals to R1. So we have that the probability of the number of collision of O with Q's hash values larger or equals to alpha m. This probability equals to the cumulative of m minus alpha m cases. I mean, for each case, for each I from alpha m to m, the probability that the collision number equals to I, right, would be well, how many ways do you have to select let's say I hash functions from in the total m? So it would be the combinatorial of selecting I from m, and this times the probability of HJO equals to HJQ for any hash function. So the probability is that's denoted as P. So it's for the I hash functions, it collides with the query, and for the rest m minus I hash functions, it does not collide with the query. All right, so this is for a single I, and we do the sum from I from alpha m to m. So here we got the probability of the number of collisions larger or equals to alpha m. All right. So this is here we got this probability, and then we define m Bernoulli random variables, say xi, where for each of them is a Bernoulli random variable, where the probability of success is 1 minus p, right? And this I from 1 to m corresponds to the m hash functions. All right. Then so we let xi equal 1 if O does not collide with Q. So it's a success. It is success for xi, not success for O. All right, so the probability is 1 minus p, and so xi equals to 0 if O collides with Q. All right, so where the probability would be p. Then the expectation of xi would be 1 minus p, right? So the number here is you use 1 times 1 minus p plus 0 times p, so you got 1 minus p, right? The expectation, right? Therefore, the expectation of the mean of x would also be 1 minus p. It's kind of straightforward. I mean, because the mean of x is equals to this, and for each of them, the expectation is 1 minus p, right? So it should be so the expectation of the mean of x is also 1 minus p. Now we define t equals to p minus alpha, and then we have so the probability of x mean minus expectation of x mean greater or equals to t. So we use the x means here and the formula here, right? And we for t it is equal to p minus alpha. So finally we would get this. So this is the probability of the sum of xi greater or equals to 1 minus alpha times m. Well, according to Hofstad's inequality, where we know that so the probability of x mean minus expectation of x mean greater or equals to t, given that each xi strictly bounded by the interval of ai and bi, so this probability would smaller or equals to e to the power of 2 n to the power of 2 and t to the power of 2 divided by there's here, and divided by sigma I from 1 to n that's bi minus ai. Right. So in our case, n is m, right? And t, as we have defined before, is p minus alpha. P minus alpha. And this bi would be 1 and ai would be 0. So each xi is from 1 to 0. So this one actually equals to this one. As you can see, n is equals to m, and this part p minus alpha is t, and this part is 1 minus 0. Sorry, yeah, this is 0. All right. So this part is m. This part is m. That's why it equals to this, and because say p is no less than p1. That's why this is smaller or equals to this. Now we consider the event that the number of collision between O and Q's hash values is no less than alpha m. So this event is equivalent to the event that O misses the collision with Q is less than 1 minus alpha times m times, right? So, which means, so xi is actually O does not collide with Q. Then so the sigma of xi is the total number of O does not collide with Q is less than 1 minus alpha times m. So the probability equals to this one, and this one here is no more than this one. So yeah, we do have a different inequality symbol here. So it is greater or equals to 1 minus the e to the power of this part. So till now we have the number of collision that is larger than alpha m, given that O, or the distance between O and Q, smaller than or equals to R1. All right. Now you can compute the case for the O with distance to Q that is larger or equals to R2 in a similar way. Then the idea of the paper is to accordingly set alpha to control false positives and false negatives. Right. So, well, this is how the paper model this probability, and also how it also we have mentioned like how it would use this model to decide the alpha. So in the project, we won't ask you to compute this alpha. We will give you alpha m. Right. So you will focus. You can just focus on the implementation part. All right, so this is the first idea in C2LSH, which is collision counting. So this idea actually solves solves this issue, right? Where concatenate k hashes is too strong. So we, instead of concatenate k hashes together, we count the number of collisions to the query. So for the second one, what if we don't have enough candidates, right? So for LSH, it may need to build multiple index or need to tune W. Right, speaking of tune W, here comes the idea in C2LSH, which is called virtual rehashing. Right. So the observation here is similar to multiprobe LSH observation, where a close point O usually falls into adjacent hash buckets of queues if it does not collide with the query, and for the same reason, right? So the idea here is why don't we, rather than recompute, rebuild the index or enlarge the W, and hence you still need to rebuild the index. Why don't we just include the adjacent hash buckets into consideration, right? So you do not need to rehash them again. Now let's give an example. So at first, we consider h1 equals to hq, where these are 10 different hash values. Right, so these are HIQ and these are HIO. Right. We have hash values of Q and O1 for different hash values. Hash functions. All right. So at first we consider HO equals to HQ, where in this case only the first one and the fifth one, they have the identical hash values. So the number of collision is 2. Right. So if we set alpha m equals to 8, then this one did not pass the test. So O1 could not become a candidate. All right. And then, as we have seen here, we include the adjacent hash buckets into consideration, right? So where the adjacent hash buckets is this and this, all right? So it's actually HIQ plus 1 and HIQ minus 1. We're back into this example. We consider HO equals to HQ plus or minus 1 if there is not enough candidates. So in this case, this one is included because it's the difference is 1, and the third one as well, also the sixth one and the ninth one. So then we have the collision number is 6, right? Is 6. Let's say alpha m is equals to 8, which means that there is still not enough collisions. And if we still have not find enough candidates as well, we need to do it the third time, right? So in this time, we consider the difference could be 2. All right. So this minus 1 and this minus 1 can be included, and the total number of collision becomes becomes 8, right? Which satisfy the condition here. All right. So I need to point point out that this idea cannot be used in original LSH. Although they do have the same observation, But if you think about it, I mean, the original LSH, for each hash, the super hash is a concatenate of a set of single LSH functions, and you need to consider each of them with +1 or -1, which in total brings you 3 to the power of k different super hashes, as we have discussed in the multi-probe LSH case. So this would brings a lot of time consumption in the query phase. So it is not infeasible to use this to apply this idea in original LSH. But in C2 LSH, because now each and every hash functions or hash values are independent, right? We don't group them or we don't concatenate them together. So there is no so the numbers won't be this large, right? Plus, we only need to recount everything. It's kind of easy and less time consuming to do. All right, so these are basically the two main ideas of C2 LSH. One is collation counting, and one is virtual rehashing. So let's have a look at the framework of using C2 LSH on nearest neighbor search. So for pre-processing part, you generate LSH functions. Right? So these functions are random normal vectors and random uniform values as AI and BI. All right. For the index part, you compute and store HI for each data object, where I is from 1 to n. So that's all. I mean, you don't need to build a hash table, because we need to count the collation to the queue, and also we need to do the hash virtual rehashing. So a hash table here won't be helpful at all. All right. So for the query part, you firstly compute the HI of Q for the query Q for different I from 1 to m. We take those O that shares or collides at least alpha m hashes with Q as candidates. All right. So if we don't get enough candidates, then we relax the collation condition. So this is the idea of virtual rehashing, one at a time. So it would be plus or minus 1, plus minus 2, plus minus 3, and so on and so forth. And then we repeat the above step, which is this step, until we got enough candidates. So this is the framework of C2 LSH, which is not very difficult to understand, and hopefully I've made everything clear. If you feel confused, please ask. All right. And in order to help you with the project, as I said, the project is to implement C2 LSH with PySpark. So here I actually gives you the pseudocode of the candidate generation part in C2 LSH, which is also what you are going to implement. Right. But please note that this pseudocode does not consider any MapReduce thing. It's just to show you the flow of candidate generation using C2 LSH. So basically, as the input, you would have the data hashes. Right. So data hashes would be n times m integers, right? Because there are n different n data. For each data, you would have m hash values, and the query hashes, which is is m integers, corresponds to the m hash functions. Alpha m, we have mentioned it quite a lot of times. It's actually the threshold of number of collision. And beta n is the minimum number of candidates. So here we use beta n because this is from the original paper. It is just to help you understand the paper, just in case you want to have a read of it. All right. So at first we set the offset to be 0, where the offset is for the virtual rehashing. We set the candidate set to be an empty set. So we will repeat this procedure until we got enough candidates. So within the while loop, we firstly, for each data with its hashes in data hashes, we do the count. We do the count thing. I will show you the pseudocode of count later. All right. So basically, for the count, we need hashes, which is from here, and query hashes is from the input, and offsets is from here. All right. So we count. If the count is larger or equals to alpha m, then we add ID into the candidate set. If it is not, then we do nothing. All right, we do nothing. Then we count the number of elements in the candidate set. If the size is still smaller than beta n, we increase our offset. Else means otherwise we have enough candidates because the size is larger or equals to beta n. Then we break. So we break the while loop and we return the candidate set as the result. All right, so this is the pseudocode for candidate generation. And for the count, right, we give the hash 1 is the data hash, and hash 2 is the query hash, but it does not matter too much. I mean, this two, they can be swapped. And offset is for the virtual rehashing, as we have mentioned before. So you set counter to be 0 at first. And for each hash 1, hash 2, one from hashes 1, one from hashes 2, we compute their difference. As long as their difference is smaller or equals to offset, we add 1 to the counter. For example, at first, the offset is 0, means you have to have, let me show it in this way. So when the offset is 0, then you should have your hash 1 equals to hash 2. And if your offset is 1, means your hash 1 is equals to hash 2 plus or minus 1. So this is the pseudocode for the count. This is the pseudocode for candidate generation. And these are what you are going to implement using PySpark. This is for your project 1. And also, I mean, this is kind of the end of the LSH part, but not the high-dimensional similarity part. We will introduce some other algorithms in week 7. Week 6 is flexibility week, means there's no lectures. All right, so we will resume our lecture in week 7. Yeah, so for rest of today's lecture, I will spend some time on the project 1, as many of you have been expecting for a long time, hopefully, right? Anyway, I mean, the spec, by the time that you are watching this video, the spec should have been already released. So I do plan to release it by the midnight of Tuesday. So the deadline would be 18th of July, and the late penalty would be the 10% on the first day and 30% on each subsequent day. This late penalty is on your raw score or raw mark. All right. For example, you delay for 2 days, then you can only have 60% of the score in your as your total score. So this will times, let's say because we have a report versus 10 marks, and we have the implementation versus 90 points. Let's say you've got 80 for your implementation. So the final score would be 54. All right, would be 54. And also it means on the 2, 3, 4 on the fifth day, you don't need to submit your implementation, your project 1, because you will get the late penalty is reduced to 0. Right. You are required to implement a light version of C2LSH, as I have mentioned a couple of times. It is just the one that we have introduced in the lecture, or more specifically the pseudocode here. All right. It is hopefully not very difficult, but still, I mean, it could be time consuming. So I urge you to start working on this as soon as possible. Don't wait for the last week or even for the last couple of days. I mean, you will see why. I mean, the evaluation is based on 2 things: correctness and efficiency. So if you work on the last couple of days, even you got it correctly, you cannot guarantee your efficiency of your implementation. And efficiency is actually important because we're talking about using PySpark. We have discussed several ways, or say bad examples and good examples of implementation in PySpark. We have discussed how transformation works, how shuffle works, for example. So you should have some idea of what should be efficient and what should not be. So avoid doing those inefficient operations. Efficiency is quite important. And also, I mean, it is possible that the algorithm could be implemented in a more efficient way. It means that you do not have to follow the pseudocode. I mean, as long as you will generate the same result as the pseudocode, you can do whatever you want. Use your own way. Probably it would be more efficient. I don't know. Right? It is for you to figure it out. All right. So you must use PySpark. Some Python modules and PySpark functions are banned. Right. So basically, the idea is one of the main purpose of this project is to use Spark to solve problems. Right. So it is meaningless, I mean, for you to circumvent PySpark, right? Or to do it in other ways. For example, you collect the data and do it in using a pure Python. It could be easier for you to write the code, but it's against the purpose of this project. So that's why we banned some PySpark functions and some Python modules, for example, like NumPy or Pandas, and also those actions, especially actions like collect or take. We do have a list. We do have a list in the spec, so you can refer to it. All right. please use transformations to process data. That's the purpose of this course. This project. Anyway, it's part of the purpose of this course. Let me see. The testing environment is the same as the environment in lab 1. So if you have not worked that lab 1 out, please do it as soon as possible. Also, I mean, if you still have met some issues or problems, ask in the piazza, and I do encourage you to help each other, because as I have mentioned before, the teaching team is really trying hard to foresee the problems and to build this environment, also to produce this lab 1 specification. But it is, impossible for the teaching team to figure out all the possible potential issues. And to be honest, many of the questions we have never seen it before, and we don't have solutions except Google it. So that's also what we can do. But we do have 300 students, and for most issues, usually more than one people will met it. And if you have solved it, and if you have seen someone's asking in the forum, please offer your help. It is really important for the whole course to operate normally, and also for the to help each other. All right. Important for all the students in the class. All right. There will be a bonus part. The maximum points that you can obtain from the bonus part is 20 out of 100. Right. This bonus part is to encourage you to implement the algorithm more efficiently. Right. We do have it's like a contest. So the first place would get all the bonus marks, and the second one will get let's say 19 points, and so on. The details is in the specification. We do encourage you to try. Right. Also, make sure you have a valid output. It happens a lot. Students put a lot of efforts, and finally he got a 0 mark or lose many of his points just because he's not output correctly. Right. So for the this project, the output should be an RDD, which contains a sequence of candidate IDs. So the output format should be easy enough for you to do it. But again, make sure you have a valid output. Make your own test cases. This is an advanced CSE course. It is not like a programming principle or database fundamental thing of database systems. So you need to have the ability to make your own test cases, just like in a real application or when you works in a company. There is no standard benchmarks for you to test your implementation. You have to create your own test unit or your own test cases in this case, right? So a real data set would be more desirable, and I'm not against you to share test cases in Piazza, right? It is okay. To share with other people. Actually, I encourage you to do so. But do remember, make your own test cases. All right. The toy example in the specification is a real toy. It's so easy, too easy to show any possible flaws in your implementation. All right. So it's like it's just for the babies. All right. You can't rely on the toy example in the spec. All right. Please make your own test cases. And also, because as I have mentioned a couple of weeks ago, we won't accept excuses. I mean, when you get a 0 mark or you didn't get what you want, saying, okay, it works on my own computer, why it does not work on yours? It's not my problem. Well, it is not my problem. All right. So it is your responsibility to make sure it works on the testing environment. Well, the testing environment is nothing special than the environment of Lab 1. And for the last thing, which is also the most important thing, don't violate the student conduct. All right. Please don't copy others' work. Don't let others copy your work. Don't show your code to any other people. Don't ask help from a ghostwriter. All right. Do it by yourself. All right. So the project should not be that difficult. I mean, should be easy enough for you to figure everything out by yourself, as long as you have understand all the things that we have discussed in the lecture. You have any problem, you ask in the forum. The teaching team would be there to help you. All right. So that's pretty much for the project and for today. So yeah, again, I mean, please start to work on the project as soon as possible. And also, we're going to release the assignment by the end of this week as well. Also, the labs, the second lab, would be released soon. Hopefully, it would help you a little bit on the project as well. All right, so that's all for today. Thank you.